Think about the device you are probably using to listen to us right now.
Yeah, that little rectangle in your pocket.
Exactly. It feels weightless in your hand, right? It feels sleek, intuitive, and, well, almost entirely detached from the physical world. I mean, it basically feels like magic.
It really does.
But to hold that device, you are actually holding the violent, explosive, and quite frankly, highly toxic culmination of nearly half the elements on the periodic table.
Which is pretty wild to think about.
It is. So today, we are going to strip away the glossy marketing of Silicon Valley and look at the actual dirt.
Ah.
But to really understand how we got here, I want to take you all the way back to a very specific moment in 2007.
The iPhone launch.
Yes. Steve Jobs is standing on a stage in San Francisco wearing his signature black turtleneck. He is holding up this little rectangle of glass and brushed metal, and the tech world is absolutely, losing its collective mind.
It was a total cultural earthquake. I mean, people were pitching tents on the sidewalks, lining up for days outside Apple stores. Some media outlets were literally calling it the Jesus phone because of the almost religious fervor surrounding its launch.
Right, and the focal point of all that worship was the screen. Jobs kept using that exact word you mentioned, magic.
Yeah, like magic.
Exactly. You tap the glass, you slide your finger, you pinch an image, and the device just responds seamlessly. But what's so fascinating in hindsight is how the old guard reacted.
What, you mean Steve Ballmer?
Yes, you had Microsoft CEO Steve Ballmer giving this now infamous interview where he openly laughed at the iPhone.
He literally chuckled at it.
He did. He pointed out that it didn't have a physical keyboard, it didn't appeal to business customers, and he confidently predicted it had, quote, no chance of gaining any significant market share.
Which has to be one of the most spectacularly wrong predictions in corporate history.
Oh, absolutely.
But you have to understand, Ballmer and many others at the time really were looking at the phone through the lens of mechanical engineering.
Right, like keyboards, tactile buttons, moving parts.
Exactly. But what Jobs understood, and what completely revolutionized our modern world, is that the future wasn't going to be mechanical. It was going to be chemical.
And that transition from the mechanical to the chemical is the core mission for this deep dive today. We are going to trace the invisible, fragile, and honestly, highly dangerous supply chains of what we are calling the rare metal age.
It's quite a journey.
We are going to follow these obscure metals from deep inside the earth, through intense corporate bottlenecks, straight into the crosshairs of global geopolitical warfare, and finally into the green technology that you, the listener, are relying on to build a sustainable future.
And to set the baseline for this journey, we first need to define what a rare metal actually is, because the terminology can be, slightly misleading.
How so? When I hear rare, I naturally assume these elements are geologically scarce, like diamonds or gold, like you have to scour the earth to find a single nugget.
Right, that's the common assumption. But that isn't always the case. Some of these metals are actually quite abundant in the Earth's crust. What makes them rare from an economic and industrial standpoint is a combination of three specific things.
Okay, what's the first one?
First, they are consumed in relatively microscopic quantities globally. We're talking maybe just hundreds or thousands of tons a year compared to the, tens of millions of tons of something like copper or iron.
Got it. So rare in terms of market volume.
Exactly. Second, they are highly specialized in their applications. And third, and perhaps most importantly, they almost never exist in concentrated veins.
So you don't just find a massive chunk of it sitting in a cave somewhere.
No, never. They are usually found only as trace byproducts, completely mixed into the ores of other, more common base metals.
So to put this into a broader historical context, the entire 20th century was defined by a massive global transition to fossil fuels, right? Coal, oil, natural gas.
Yeah, entire empires rose and fell based on who controlled the oil fields.
Right.
Right.
But what we are looking at today is a transition away from a hydrocarbon-based economy to an economy entirely dependent on these obscure corners of the periodic table.
Absolutely.
And to see that shift, we don't need to look at an oil derrick. We just need to look right back at your pocket.
Okay.
Because if we break down the anatomy of your smartphone based on the source material we're looking at, it reads less like an electronics manual and much more like an advanced chemistry textbook.
It really is a marvel of material science. Let's take that magical glass screen that Steve Jobs was touting.
The one that responds to touch.
Right. The reason your phone knows exactly where your finger is tapping isn't because of the glass itself. Glass is an insulator. It blocks electricity.
Okay, so what's doing the tracking?
The magic happens because of a microscopic layer of a rare metal called indium. Specifically, it's formulated into something called indium tin oxide.
And how exactly does that work? Why use indium?
Well, indium has this very unique property. It can be engineered to be completely transparent while remaining highly conductive to electricity.
Oh, wow. So you can see right through it, but it still carries a charge.
Precisely. So manufacturers lay down a nearly invisible grid of indium tin oxide across the screen. And because the human body naturally carries a tiny electrical charge,
Right, bioelectricity.
exactly. The moment your finger touches the glass, it alters the electrical field of that transparent indium grid. The phone's processor reads that tiny disturbance, calculates the exact X and Y coordinates of your finger, and translates that into a tap or swipe.
That is incredible. So indium is basically the invisible wire linking your nervous system to the digital world.
That's a great way to put it, yeah.
And the visual output on that screen, like the incredibly vibrant high-definition colors you see when you're scrolling through photos or watching a video, that requires a completely different set of elements, right?
It does. To get those brilliant, rich screen hues, the device relies on a dusting of elements like europium and terbium.
Europium and terbium. Oh,
Yeah, they belong to a specific group known as the rare earth elements. What makes them special is their atomic structure. When you stimulate europium and terbium with electricity, their electrons get excited and jump to higher energy states.
like they get electrically charged up.
Right. And when they drop back down to their normal state, they release that extra energy as photons, specifically highly pure, intense wavelengths of red and green light.
So without that specific chemical dusting, your high-definition display would look, what, really washed out and dull.
Exactly. You wouldn't have anywhere near the color accuracy or vibrancy we're used to today.
Okay, so we have indium tracking our touch, europium and terbium projecting the colors. But a phone is ultimately a communication device. It has to manage an incredible amount of electrical noise and power to stay connected to a cell tower miles away.
Right. Power management is huge.
How does it handle that without massive, bulky power regulators?
That brings us to tantalum. Inside your phone, there are these tiny components called capacitors. You can think of a capacitor as like a microscopic dam that holds back electrical current, releasing it in precise, steady streams so the delicate microchips don't get fried.
Sort of regulating the flow of electricity.
Exactly. Now, for decades, capacitors were relatively bulky, but tantalum changed everything. Tantalum has this extraordinary ability to form an ultra-thin, highly stable, protective oxide layer on its surface.
And why does a thin layer matter so much?
Because this insulating layer is incredibly thin. I mean, we are talking nanometers. You can pack a massive amount of electrical storage capacity into a microscopic space.
Oh, I see.
Yeah. Tantalum is the reason your phone doesn't drop calls while managing power surges, and it's the reason the phone can be a quarter-inch thick instead of the size of a shoebox.
And then, of course, driving all of this, you have lithium forming the chemical basis of the battery storage, making the entire system mobile.
Right, the power source.
What blows my mind is that even the manufacturing process itself relies heavily on these trace elements before the phone is even put together. The source material highlights cerium, which is used to polish the glass. But it's not just grinding it down like sandpaper, is it?
No, it's much more sophisticated than that. It's a process called chemical-mechanical planarization.
That sounds intense.
It is. Cerium oxide doesn't just physically scratch the glass smooth. It actually reacts chemically with the silicon dioxide in the glass. It binds to the surface atoms and sweeps them away, buffing the glass perfectly smooth down to a molecular level.
A molecular level.
Yes. This ensures there are zero microscopic imperfections that could distort the light coming from those europium and terbium phosphors we talked about.
Looking at all this, it reminds me of a brilliant analogy regarding the chemical corporation BASF.
Oh, I know the one you mean.
Yeah, they had this famous marketing slogan in the 1990s. We don't make a lot of the products you buy. We make a lot of the products you buy better.
Yes, exactly.
That perfectly encapsulates the role of rare metals in the modern economy. These elements don't form the bulk structure of our devices. They are the invisible enablers. They make things smaller, faster, more vibrant, and exponentially more powerful.
It is the ultimate expression of the BASF principle. And the sheer volume of elements we now rely on is a profound shift in human history.
Give me some perspective on that.
Well, if you look at the 1960s, the average American home, with its rotary phones, basic cathode ray televisions, and mechanical appliances, relied on maybe 20 elements from the periodic table in total.
20. Yeah.
Today, if you just look at a single Intel computer chip, it utilizes nearly 60 different elements.
Wow, just the chip.
Just the chip. We are harvesting a complete palette of materials that metallurgists and scientists just a few decades ago literally threw away, dismissing them as annoying impurities in the rock.
So to put it in everyday terms, rare metals are basically the yeast in pizza dough.
I love that analogy.
Right. You only need a microscopic amount, a tiny pinch. But without that yeast, you don't have a pizza. You just have a flat, dense, useless cracker.
Exactly.
Which brings up a massive, glaring question. If we are only using a fraction of a gram of tantalum or a tiny dusting of europium per phone, why are we facing such severe global supply risks? How on earth can we run out of something we only use in such microscopic pinches?
That is the central paradox of the rare metal age. And the answer really comes down to two forces: velocity and scale.
Velocity and scale. Break that down for me.
Well, product life cycles have accelerated at a dizzying, unprecedented pace. Think back to 1983, when Motorola released the first commercially available mobile phone, the Dynatac 8000X.
Oh yeah, the classic brick phone.
Exactly. It was essentially a plastic brick. It weighed almost a kilogram, took 10 hours to charge for 30 minutes of talk time, and it cost nearly $4,000.
Right, so the market for that device was incredibly niche. It was a status symbol for Wall Street executives and wealthy real estate developers. It wasn't a daily necessity for the average citizen.
Precisely. But fast forward to today. We don't have a few thousand executives walking around with brick phones. We have billions of human beings relying on smartphones for absolutely everything.
Everyone has one.
So even if there is only a fraction of a gram of a certain rare metal in one device, when you multiply that microscopic amount by 3 or 4 billion units, the aggregate demand becomes staggering.
The multiplication factor is just terrifying when you actually do the math.
And it's not just the number of phones, it's the increasing complexity of each new generation. Take the element gallium, for example.
What happened with gallium?
When the global telecom industry transitioned from 3G networks to 4G networks, those new 4G smartphones required 6 to 10 times more gallium than the older models.
Wait, really? Why did they need so much more? What was the gallium actually doing?
Gallium is used in radio frequency power amplifiers. Because 4G networks transmitted vastly more data at higher frequencies, the phones needed a semiconductor material that could handle higher power levels and switch on and off billions of times a second without overheating.
So the older materials couldn't handle the heat.
Right. Silicon couldn't handle the thermal stress efficiently, but gallium arsenide could. So overnight, the demand for gallium skyrocketed. Or look at battery technology. The average smartphone battery contains roughly 6 grams of cobalt.
6 grams sounds like nothing. That's, what, the weight of a couple of pennies?
Exactly. But when you aggregate that globally, it equates to 7,500 tons of refined cobalt consumed every single year just to keep our smartphones powered.
That sheer scale fundamentally shifts how you view the modern world. I mean, if your entire digital existence, your banking, your navigation, your family photos, your ability to communicate in an emergency, depends on a continuous, uninterrupted sprinkle of these trace elements, the obvious next question you have to ask is, where exactly do we get this dirt?
And that's where the story gets really complicated.
Because mining these elements is not some open, competitive, free market utopia where anyone with a shovel can strike it rich. It is a world of extreme, almost unbelievable bottlenecks.
To truly understand the nature of these bottlenecks, we have to travel to a small, unassuming town in the state of Minas Gerais, Brazil, called Araxá.
The contrast in Araxá is incredibly cinematic according to the source material. Picture this lush, verdant tropical region of Brazil. Nestled in these hills is a sprawling, decaying, colonial-style resort called the Hotel e Termas de Araxá.
Yeah, it was built back in the 1940s.
Right, by a Brazilian president, with the express goal of attracting international high society to its naturally radioactive thermal spas. It is a monument to faded luxury. It boasts an incredible 3-story rotunda with a massive stained glass ceiling, expansive black and white marble floors, sweeping verandas. But today, it basically feels like a ghost town.
Grass is literally growing through the cracks in the sidewalks.
Exactly. Out of nearly 300 opulent rooms, maybe 15 are occupied on any given night. The golden age of thermal spa tourism is long dead.
But, and this is the crazy part, If you walk right across the parking lot from this crumbling relic of the 1940s, you step into a completely different
It's
universe.
like a time warp.
You find yourself on a sprawling, immaculately manicured, state-of-the-art corporate campus. It looks exactly like a high-tech corporate park in Silicon Valley. The streets are lined with pristine palm trees, the workers are all wearing matching clean jumpsuits, and the facilities are cutting edge.
So what is this place?
This is the headquarters of CBMM Companhia Brasileira de Metalurgia e Mineração. And the irony is, CBMM is located there for the exact same geological reason that the thermal hot springs exist. They are both sitting on top of a massive, ancient volcanic caldera.
Right. Millions of years ago, magma seeped up through the Earth's crust here, and as it cooled, it left behind a mineral complex that is mind-bogglingly rich. Specifically, it is rich in a soft granite gray metal called niobium.
Niobium.
And the scale of CBM's dominance over this metal is almost hard to comprehend. They don't just participate in the niobium market, they basically are the market. This single company, operating out of the single volcanic crater in Brazil, produces 85% of the world's supply of niobium.
One company controlling 85% of a vital global resource is a level of market concentration that would make standard oil monopolists blush.
It's insane.
But the way CBMM achieved this monopoly wasn't through ruthless hostile takeovers or political thuggery. It is actually a masterclass in long-term visionary corporate strategy. Because back in the 1950s, when they first discovered the deposit, nobody really wanted niobium.
Wait, why not? If it's so vital today, why was it useless in the 1950s?
Well, mainly because of the difficulty in refining it and a lack of applied knowledge. Metallurgists knew niobium had fascinating theoretical properties, specifically that it could strengthen steel while making it lighter and more heat-resistant.
Okay, that sounds pretty useful.
It does, but extracting it from the host rock was incredibly difficult, and steelmakers were perfectly happy using cheaper, well-understood alloys like manganese or vanadium. CBM had an asset that the market simply didn't value, so they basically had to create the global market from scratch.
How do you even do that?
They spent decades quietly investing in metallurgical research, improving their extraction processes to drive the price down, and then proactively sending scientists around the world to convince skeptical steel manufacturers to just try adding their product.
And when those manufacturers finally tried it, the superpower of niobium became impossible to ignore, because the efficiency gains are staggering. If you add just a tiny pinch of niobium, we're talking maybe 100 to 200 grams, to an entire ton of steel, you fundamentally alter its structural integrity. You massively increase its strength.
The strength-to-weight ratio goes off the charts.
Right. To give you a concrete, real-world picture of what that means, when Gustav Eiffel built the Eiffel Tower in the late 19th century, it required 7,000 tons of basic structural steel. If an architectural firm wanted to build an exact, full-scale replica of the Eiffel Tower today using modern, niobium-strengthened steel, they would only need 2,000 tons of material.
The physics behind that weight reduction is just fascinating.
Tell me about it.
When you melt steel and add that tiny pinch of niobium, the niobium atoms form microscopic compounds called carbides and carbonitrides. These compounds act like tiny, indestructible roadblocks along the grain boundaries of the steel.
Roadblock.
Yeah. When the steel is put under immense physical stress, its internal crystalline structure wants to slide into form. But the niobium compounds pin the grain boundaries in place, preventing the microscopic sliding that leads to metal fatigue and failure.
That is wild.
That mechanism changes the entire landscape of global infrastructure and manufacturing. Modern suspension bridges, high-pressure oil pipelines, the chassis of your car, they all rely on niobium alloyed steel to be radically lighter, which saves fuel while remaining incredibly strong to save lives.
And CDMM hit the geological lottery. Not only is their niobium deposit incredibly rich in concentration, but the rock itself has been weathered over millions of years into loose lateritic soil.
Which is a massive competitive advantage.
Exactly. When we think of mining, we think of massive explosive charges and giant crushers grinding solid granite into dust, which requires an astronomical amount of electricity and money. But CBM doesn't have to grind hard rock. They are basically scooping up highly concentrated dirt.
It's just sitting there.
Their production costs are unbelievably low, and their reserves are estimated to be large enough to supply the entire planet for the next 200 years.
Which naturally makes them obscenely predictably profitable. They are a private company owned by a single Brazilian family, the Moreira Salles family, who are worth billions. CBMM reportedly operates with a net income profit margin hovering around 37%, clearing well over $600 million in pure profit annually. They are an economic fortress.
This brings me to a scenario that the source material explores, which I find darkly hilarious. Let's say I am an ambitious junior mining executive. I'm exploring in North America or Africa, and my geologists strike gold well. They strike niobium. We find a new unexploited deposit. How on earth do I compete with a sprawling, debt-free, multi-billion-dollar Brazilian fortress that has a 50-year head start?
The brutal reality of the mining industry is you usually don't. Junior mining companies face an absolute nightmare scenario when trying to break into these specialized rare metal markets. The text highlights a company called Tioman Resources as a cautionary tale.
What happened to them?
Back in 1995, Tioman discovered a rich mineral deposit in Kenya. They had the maps, they had the ore, but finding the dirt is the easy part. Over the next decade, they had to fight through a labyrinth of environmental assessments, deal with fierce local political opposition, negotiate port access, and constantly try to raise capital while global financial crises caused commodity prices to wildly fluctuate.
So they were just bleeding money for years.
Exactly. More than 10 years after the discovery, the CEO finally had to step down and the project was still stalling in the mud.
Or look at another example from the sources, Avalon Rare Metals. They found a significant deposit up in northern Canada near the Arctic Circle. They have a solid plan and a massive reserve. But think about the logistics. They are digging through frozen tundra. They have to build their own roads, their own power plants, their own water treatment facilities, and import all their heavy machinery and labor into one of the most hostile environments on Earth.
It's a logistical nightmare.
It costs hundreds of millions of dollars in upfront capital expenditure before they can even extract and sell a single ounce of processed metal.
And this brings us to the most terrifying metric in the entire industry: the lead time. On average, it takes 15 years to take a rare metal mine from the initial geological discovery to actual commercial-scale production.
15 years. Let that sink in.
Yeah, 15 years.
That means the obscure trace metals trickling out of a brand new mine today had to be planned, financed, and permitted back in 2011. You are essentially asking mining executives to risk billions of dollars predicting the highly specific material demands of a technological future they cannot possibly imagine. They have to guess what Apple or Tesla will need a decade and a half before the product is even conceptualized.
Exactly. And while public junior mining companies are constantly distracted, hosting quarterly investor calls, desperately justifying their sagging stock prices, and scraping together high-interest funding just to keep the lights on, a private, entrenched monopoly like CBMM just quietly scoops up its loose dirt. They refine their product and organically expand their massive market share without ever having to answer to the impatience of Wall Street.
Okay, I want to pause and push back on this dynamic for a moment. Because culturally, whenever we hear the word monopoly, all our warning sirens go off.
Naturally.
We are conditioned to believe monopolies are inherently terrible for the consumer. We picture price gouging, stagnation, terrible working conditions, a total lack of innovation. But when you look objectively at CBMM, they seem incredibly efficient. Their campus is beautifully maintained, they have rigorous environmental certifications, their workers are highly paid and well taken care of.
They're a model employer in many ways.
Right. And most importantly, they provide a completely stable, predictable supply of a crucial metal at a price that global steelmakers are perfectly happy with. In a world of highly volatile, chaotic, high-tech supply chains, isn't a benevolent, efficiently run monopoly actually vastly superior to relying on 100 chaotic, underfunded, and environmentally risky junior mines scattered across the globe?
It is a very compelling, pragmatic argument. And if you strictly look at the Araxa operation in a vacuum, it certainly appears that way. Stability and predictability are the holy grails of global manufacturing. But the systemic danger doesn't come from malevolence. It comes from the inherent fragility of a single point of failure.
A single point of failure.
Yes. The United States government is acutely aware of this vulnerability. In fact, they officially list the CBMM mine in Brazil as critical infrastructure located abroad.
Wow, they actually label it critical infrastructure.
They did. Why? Because if there were an unforeseen catastrophe, a massive localized natural disaster, a sudden political upheaval in Brazil, a labor strike, or a drastic change in export tariffs, the global steel, aerospace, and tech industries would face an immediate catastrophic bottleneck. They would have nowhere else to turn. Relying on one single crater in the earth for 85% of anything is a massive systemic risk, regardless of how beautifully manicured the corporate campus is.
That makes perfect sense. The vulnerability isn't in their current behavior. It's in the lack of an alternative if things go wrong. And what's truly sobering, according to the text, is that the situation in Brazil is actually the best-case scenario. It is the sunny, straightforward anomaly of the rare metal world,
Oh, absolutely.
because finding the rock and digging it up is only about 10% of the battle. The real nightmare, the part that keeps material scientists and chemical engineers awake at night in a cold sweat, is the process of separating the rare metal from the host rock. And to understand the sheer horror of that process, we have to leave the warm green hills of Brazil and travel to a freezing radioactive relic of the Soviet Union.
Right. We are heading to the Baltic coast to a town called Sillamäe in Estonia.
Sillamäe is a wild, almost dystopian setting. It sits right on the freezing, windswept coast of the Baltic Sea, just about 30 kilometers from the Russian border. For decades during the Cold War, Sillamäe essentially did not exist.
It was wiped off the map.
Literally, it was a closed Soviet city. It wasn't printed on public maps. There were no road signs pointing to it. You couldn't just visit. The Soviet Union built this entire town for one specific purpose: to service a massive, highly secretive facility known simply as Factory Number 7.
Very ominous.
And today, that facility is a private company called Silmet. During the height of the Cold War, the scientists and workers locked inside Factory Number 7 were engaged in top-secret metallurgical processing, heavily focused on refining uranium to feed the Soviet nuclear weapons program.
But eventually, the local uranium ore ran out. To keep the facility running, the Soviets started importing different ores from the Kola Peninsula. These imported ores contained the uranium they needed, but they also contained a complex soup of chemical impurities, elements like niobium, tantalum, and the elusive rare earth elements.
The stuff that usually just gets thrown away.
Right, normally miners throw impurities onto a slag heap. But the Soviet military complex was highly pragmatic. They realized that these specific trace elements were becoming absolutely crucial for advanced aerospace engineering, radar systems, and defense technologies. So instead of throwing them away, they repurposed segments of Factory Number 7, building complex, hazardous processing lines to chemically extract these valuable trace metals.
And the process of extracting them is where we need to dive deep into the chemistry, because it is horrifyingly complex. When the average person thinks of mining, we picture a guy with a pickaxe hitting a rock wall until a shiny chunk of gold or silver falls out. We think of mechanical separation.
Like panning for gold.
Exactly. But rare metals do not work like that. They don't exist in shiny, isolated chunks. They are intimately woven into the atomic structure of the host rock. Refining them isn't a mechanical process. It is a series of violent chemical creations and destructions.
That's a crucial distinction. The industry terms for this are beneficiation, cracking, extracting, and separating. You don't just crush the rock, you have to pulverize it into a fine powder, roast it at blistering temperatures in giant kilns, and then dilute it in massive churning vats of highly corrosive acids.
It sounds like a literal witch's brew.
It basically is. You are effectively attempting to break the molecular bonds of the Earth itself. It requires a constant, delicate balancing act of time, temperature, and caustic liquids to selectively strip away the elements you don't want while keeping the specific trace elements you do want suspended in the solution.
And the margin for error is essentially zero. There is a quote in the source text from a rare earth tech CEO that is absolutely chilling. He says, point blank, if you make a mistake, you're dead.
Wow.
And he isn't being dramatic or speaking metaphorically. He is talking about the physical reality of the metallurgy. The text describes an incident in Massachusetts where a massive 55-ton furnace, which was used to apply extreme heat and pressure to highly reactive metals, literally exploded.
A 55-ton furnace exploding.
Yes. It was catastrophic. It sent 3 tons of solid metal shrapnel flying a quarter-mile away. Or there are countless instances of factories spontaneously catching fire because the microscopic dust generated during the milling of these volatile metals is highly pyrophoric.
Meaning it catches fire on its own.
Exactly. It can ignite simply upon contact with the oxygen in the air.
And even if you manage to avoid a catastrophic explosion, the chemistry itself is incredibly unforgiving, especially when dealing with the rare earth elements. Let me explain why this is a chemist's worst nightmare.
Please do.
The rare earth elements, the lanthanide series on the periodic table, are notoriously difficult to separate because their atomic structures are virtually identical. Think of them like a group of identical twins.
Okay, identical twins.
The only difference between element A and element B is deeply buried in their inner electron shells. Chemically, they look and behave almost exactly the same. So when you dump them into an acid bath, they all react identically. They bond tightly to one another.
So you can't just easily fish one out.
No, not at all. To separate them, you can't just run them through one chemical reaction. You have to run the solution through hundreds, sometimes thousands, of successive solvent extraction cascades, incrementally nudging the purity level up a tiny fraction of a percent at a time.
And what happens if the delicate balance in those vats gets thrown off? Say someone turns a valve too far.
Disaster. If you add just a little too much sulfuric acid during the extraction phase, the pH balance plummets. Instead of selectively dissolving the target metals, the acid aggressively dissolves entirely too many minerals from the host rock at once, including naturally occurring radioactive elements like thorium or uranium.
Oh, man.
Yeah. The entire mixture instantly coagulates and turns into a useless, highly radioactive, highly toxic, viscous, brackish blob. You can't reverse the reaction, the batch is completely ruined, and now you have to figure out how to safely dispose of a vat of radioactive sludge.
If I am tracking the chemistry correctly, refining these rare earths is basically like trying to unbake a cake. You are given a fully baked, finished cake, and your boss tells you to chemically extract the exact amount of sugar back out of the big flour.
That's a brilliant way to picture it.
But in this scenario, the flour is highly radioactive, the sugar is chemically bonded to the eggs, and if you turn the heat up too high, the oven violently explodes.
That is an incredibly vivid, accurate, and terrifying analogy. That is exactly what the metallurgists at Silmet are doing every single day.
And right in the middle of this decaying post-Soviet factory, with its labyrinth of outdated pipes meandering overhead like some grim M.C. Escher painting, is a guy named David Obrock. His story is fascinating. He isn't a former Soviet apparatchik. He's a guy who grew up on a farm in rural Ohio.
Talk about a fish out of water. Seriously.
Yeah.
And now he is the CEO running this immense hazardous facility. He is out there managing these chaotic, temperamental production lines of rare earths, niobium, and tantalum, constantly fighting to keep the aging infrastructure working just so they can produce a meager 3% of the world's rare earth supply.
And that 3% figure is the most vital statistic in this entire section. You have to ask yourself, why is an outdated factory in Estonia one of the only places outside of Asia doing this?
Very good question.
The answer is brutal economics and environmental reality. Because producing these metals is so inherently toxic, so incredibly capital intensive, and so technically fraught, very few developed nations actually want to do it. It is the ultimate global scale manifestation of not in my backyard.
NIMBY on a planetary scale.
Exactly. The wealthy, tech-hungry nations of the West essentially looked at the acid baths, the radioactive sludge, and the exploding furnaces, and decided to intentionally outsource this dangerous alchemy. They found one specific nation that was willing to endure catastrophic environmental degradation in exchange for securing total global market dominance: China.
Exactly. China strategically absorbed the burden of refining these materials when the rest of the world walked away. But when you willfully outsource over 90% of the foundational supply chain of the modern world to a single geopolitical rival, you hand them an unprecedented, almost invincible trump card.
Which brings us to the pivotal moment when that trump card was finally played. And I want to set the stage carefully here. It is vital to look at the next historical event purely through the lens of supply chain economics and resource dependency.
Right, keeping it strictly to the material facts.
Exactly. The incident involves complex, deeply rooted, and heavily disputed sovereignty claims over a cluster of islands in the East China Sea. We are completely setting aside the politics of those claims. We're not validating any national borders or endorsing any geopolitical maneuvers. Because regardless of the politics, the material facts of what happened to the global technology market in September 2010 serve as the ultimate terrifying case study in exactly how fragile our modern world really is.
It is a textbook example of asymmetric economic warfare. The catalyst occurred on the morning of September 7, 2010.
Right. There's an uninhabited cluster of islands, which are known as the Senkaku Islands in Japan and the Diaoyu Islands in China. Both nations claim historical sovereignty, and nationalist tensions regarding the fishing rights and territorial waters around these islands have simmered for decades. On this particular morning, a Chinese fishing trawler collided with two Japanese Coast Guard patrol vessels near the islands.
The physical collision immediately sparked a massive diplomatic crisis. The Japanese Coast Guard boarded the trawler, arrested the Chinese captain, and detained him in Japan. Beijing was furious. They demanded his immediate and unconditional release.
So things escalated quickly.
Oh, incredibly fast. Diplomatic channels rapidly froze. Ministerial meetings were canceled. And then, away from the loud public posturing, something unprecedented and entirely silent happened deep within the global supply chain.
On September 21st, Japanese tech executives and trading houses started panicking. They reported that China was suddenly refusing to fill any orders for rare earth elements. All 32 of China's authorized rare earth export companies mysteriously and simultaneously halted all trade with Japan on the exact same day.
And this is where the leverage becomes apparent. Beijing never officially announced an export embargo. They never issued a public decree stating they were weaponizing rare metals. The customs officials simply stopped processing the paperwork.
The shipments just sat on the docks.
Exactly. And because Japan is a colossal hub for high-tech manufacturing, producing the world's finest electronics, automotive components, and advanced magnets, they were uniquely vulnerable. They relied on China for more than half of their total rare earth imports.
The impact on the Japanese economy was devastating and immediate. Entire manufacturing sectors were effectively paralyzed. Without a continuous feed of these trace elements, assembly lines ground to a halt. And the panic wasn't contained to Tokyo. The global commodity markets completely lost their mind.
Oh, prices went absolutely through the roof.
Prices for specific rare earths didn't just tick up, they exploded. Over the next year and a half, the prices for some critical elements spiked by up to 2,000%. Japan eventually succumbed to the pressure and released the fishing boat captain, but the damage was done. The illusion that the global tech industry operated on a stable, apolitical supply chain was permanently shattered.
To truly understand the tragic irony of this vulnerability, we have to introduce a brilliant Japanese materials scientist named Masato Sagawa. His story perfectly encapsulates the trap of the rare metal age.
What's his connection to all this?
Well, in the late 1970s, Sagawa was a researcher at the Japanese tech giant Fujitsu. At the time, the entire electronics industry relied heavily on cobalt, specifically sourced from the Congo, which was then called Zaire to manufacture permanent magnets. But then, intense civil conflict broke out in Zaire. The mine shut down, cobalt prices skyrocketed, and global supply was choked off.
So they needed an alternative fast.
Right. Sagawa was essentially tasked with a seemingly impossible mission: invent a completely new type of powerful magnet that bypasses the need for Congolese cobalt.
And against all odds, working in his lab, he actually did it. He invented the neodymium iron boron magnet, which is widely considered one of the most important material breakthroughs of the late 20th century. It was revolutionary.
It was a stroke of pure physical genius. Sagawa realized that neodymium and iron had incredible magnetic potential, but the iron atoms sat too closely together. So he wedged tiny boron atoms between the iron atoms.
The spacing them out.
Exactly. This microscopic spacing altered the crystalline structure just enough to create a magnetic field exponentially stronger than anything that had existed before. This specific magnet is the fundamental technology that makes your smartphone vibrate, that allows hard drives to spin at high speeds, and that powers the tiny speakers in your wireless earbuds.
So it was a massive success.
It was, but as with all things in chemistry, there was a catch.
And it was a massive faithful catch. While Sagawa's new magnet was incredibly powerful at room temperature, it had a fatal flaw. It lost its magnetism when it got too hot.
Which is a huge problem.
Yeah, a huge problem, yes. If you want to put that magnet inside a high-performance electric car motor or an industrial wind turbine, which generate immense heat, it fails. To stabilize the magnetic domains at high temperatures, Sagawa had to tweak his recipe. He added a small amount of a heavy rare earth element called dysprosium.
Dysprosium.
Yes. He viewed it as a minor, temporary chemical fix to make the magnet commercially viable. But by adding dysprosium, he inadvertently shifted Japan's entire resource dependency. He successfully escaped the bottleneck of cobalt in the Congo, only to walk his country directly into a much tighter, much more powerful bottleneck, heavy rare earths strictly controlled by China.
It's wild. He spent years in a lab solving one geopolitical crisis, only to accidentally engineer the exact vulnerability that would bring his country's tech sector to its knees decades later. It's a tragedy of unintended consequences.
And this brings up a massive analytical question regarding that 2010 embargo. Look at the speed and coordination of the Chinese response. Did China really just pull the plug on the global high-tech economy overnight in a fit of sudden anger over a single fishing boat captain? Or was this embargo actually the culmination of a long-term, highly calculated economic strategy that had been quietly building for decades, just waiting for a convenient geopolitical excuse to finally show its teeth?
Every piece of evidence in the source material strongly points to the latter. The foundation for this dominance was openly declared decades earlier. In 1992, the paramount Chinese leader Deng Xiaoping made a very famous, incredibly prescient statement. He said, There is oil in the Middle East. There is rare earth in China.
That is a bold statement.
It was a clear strategic recognition that the future of global power would not be determined by hydrocarbons, but by the periodic table.
And the execution of their strategy over the following decades was ruthlessly brilliant. Phase 1 was dominance through pricing. For years, China aggressively mined and refined rare metals, aided by vastly lower labor costs and an almost total disregard for environmental regulations. They flooded the global market with cheap rare earths, selling them at a 50 to 60% discount compared to Western producers.
Which is an impossible price point to beat.
American and European mines simply couldn't compete with those rock-bottom prices. It cost them more to extract the rock than they could sell it for. So, one by one, Western mines went bankrupt and shuttered their operations.
That was the trap. Once the Western domestic supply was completely dead, China initiated Phase 2. They evolved from being a cheap exporter of dirt to an economic superpower. They realized that simply digging up raw ore and selling it for a few dollars a pound was a massive lost economic opportunity. The real wealth isn't in the dirt, it's in the finished product.
So what do they do?
Beijing started implementing strict export quotas. They artificially restricted the amount of raw, rare earth materials that were legally allowed to leave Chinese borders.
Which created a brilliant, inescapable ultimatum for the West. If a massive tech conglomerate in Japan, or the United States, or Germany wanted guaranteed, affordable access to these critical elements, they couldn't just import the raw materials anymore. The only way to ensure their supply lines survived was to physically pack up their advanced manufacturing plants and relocate them inside China's borders.
It was a brilliantly calculated, multi-decade maneuver to capture not just the billion-dollar mining industry, but to forcibly absorb the multi-trillion-dollar high-tech manufacturing base of the entire world.
And the 2010 embargo was simply the moment the trap snapped shut. It proved to the world that the leverage was absolute. But what makes this story truly sobering is that the panic wasn't confined to consumer electronics executives in Tokyo worrying about flat-screen TVs and smartphones. The shockwaves from that embargo violently rattled the halls of the Pentagon in Washington, D.C.
Oh, absolutely.
Because the terrifying reality is that the exact same tiny, ultra-powerful magnets that Masato Sagawa invented to make your smartphone vibrate are the exact same magnets required to steer smart missiles.
And again, keeping strictly to the material science and supply chain economics, we have to look at how modern military power is actually generated. The fundamental nature of warfare has evolved from relying on brute, hard metals to relying entirely on highly sensitive smart metals.
Let's trace that historical context because it's fascinating. If you go back to before World War I, warfare was essentially about manpower, basic iron, and logistics. But as conflict became mechanized, metallurgy became the ultimate deciding factor. Take an obscure rare metal like tungsten.
Tungsten was a game changer.
It really was. During World War I, metallurgists realized that if you added tungsten to steel, you created high-speed steel. Before tungsten, if a machinist was cutting and shaping a steel axle for a military vehicle, it took roughly 660 minutes. Because if the cutting tool got too hot, it would warp and fail.
Right, the friction would just destroy it.
But a cutting tool made of tungsten alloyed steel could withstand blistering heat. Suddenly, that same steel axle could be cut in just 40 minutes. It was an exponential leap in manufacturing output. It was such a massive strategic advantage that the U.S. government deemed it literal treason to export tungsten to enemy nations.
By the time World War II erupted, metallurgy was at the absolute forefront of military strategy. You had the United States and Germany engaging in intense, covert bidding wars over minor metals in neutral countries like Spain and Portugal.
Like trying to buy up all the supply.
Exactly. Intentionally driving up the prices of trace elements 20-fold, not necessarily because they needed them, but simply to financially starve the other side of the resources required to build advanced weaponry. Germany, in particular, despite having very poor domestic geological resources, developed a vastly superior metallurgical strategy. They expertly secured specific alloys from across the globe to build highly advanced, durable weapon systems.
Fast forward to today, and the battlefield isn't just mechanized. It is entirely electronic and autonomous. Look at a complex system like Israel's Iron Dome. This is a system designed to track and intercept incoming rockets, moving at supersonic speeds, and it has to make those calculations in milliseconds. How does it physically do that?
It is completely dependent on the periodic table.
Yes. It uses specific rare earths in the fin actuators to physically steer the interceptor missiles with microscopic precision. It uses indium in the command and control touchscreens. It relies on complex microchips packed with minor metals to crunch the trajectory data.
Or consider the crown jewel of American air power, the F-35 Lightning II stealth fighter. That single aircraft is essentially a flying, highly weaponized periodic table.
A flying periodic table. I like that.
A single F-35 requires approximately 920 pounds of specific rare earth materials to function.
Almost 1,000 pounds per jet.
Yep. The airframe is heavily reliant on titanium because it needs to be incredibly light to maintain agility, but also highly heat-resistant to survive the friction of supersonic flight. The literal nuts and bolts holding the delicate internal systems together are made of beryllium.
Why beryllium?
Because beryllium is exceptionally lightweight, dissipates heat rapidly, and crucially, it doesn't spark. The advanced targeting radar, which allows the pilot to see enemy aircraft miles away, relies on gallium to amplify the signals without melting the electronics. The laser targeting systems and the intricate cockpit displays are entirely dependent on tantalum capacitors managing the electrical loads.
And this is exactly where the shockwave of the 2010 Chinese embargo hit the Pentagon. In 2011, Congress essentially forced the Department of Defense to conduct a comprehensive audit of its critical material supply chain. And the Pentagon came back with a terrifying realization.
They didn't fully understand it.
Exactly. The complexity of these modern multi-tiered weapon systems is so incredibly deep, and the subcontractors are so highly specialized, that physically tracing every single trace element back to the specific hole in the ground it originally came from was nearly impossible.
The opacity of the supply chain is a massive vulnerability because in the military world, you can't just casually swap out a material if a supply line gets severed. Commercial companies can pivot, but military specifications are unbelievably rigid.
How rigid we're talking?
If a defense contractor wants to introduce a slightly different metal alloy into the wing of a jet fighter, it can take up to 20 years of rigorous testing. They have to prove beyond a shadow of a doubt that the new material won't warp, crack, corrode, or catastrophically fail when the airframe is pulling extreme G-forces at Mach 4. They are locked into the specific chemistry of the materials they use.
Okay, I have to jump in here and heavily push back on this because it feels like we are ignoring the most obvious solution.
Yeah.
We are talking about the United States military. They operate with an essentially unlimited budget. If the Pentagon knows that they absolutely require these specific trace metals to build their jets, and they know the global supply chain is completely vulnerable to foreign embargoes, why don't they just solve the problem with cash? Why can't they just buy a massive, multi-decade supply of raw, rare earth ore on the open market, ship it to Nevada, and stockpile it in a giant warehouse, exactly like they stockpiled materials during the Cold War? Just buy the dirt and sit on it. Problem solved, right?
It is a completely logical thought process, and it is exactly the kind of blunt force solution that politicians often suggest. But stockpiling rare metals does not work the same way as stockpiling crude oil or wheat. You can't just pile raw ore in a warehouse and consider yourself secure.
Why not?
Because the defense contractors building these jets don't just need generic rare earths. They require dozens of highly specific, heavily processed, chemically tuned grades of magnetic powders and alloys.
But if you have the raw ore, can't you just make the specific powders when you need them?
Not if you don't have the factories. And that is the crux of the issue. Over the last 3 decades, as the West outsourced the toxic extraction processes to China, they didn't just lose the mines. They lost the entire midstream processing infrastructure.
I see.
Yeah, they lost the specialized chemical plants, the intellectual property, and the generations of skilled metallurgists who actually know how to turn raw dirt into military-grade components. If the U.S. government stockpiles millions of tons of raw, rare earth ore, but doesn't have the domestic multi-billion-dollar processing facilities required to refine and separate that ore into high-purity grades, the raw dirt is functionally useless.
That's a huge problem.
It is exactly like stockpiling 10 million cans of tuna in your basement to survive the apocalypse, but forgetting to buy a can opener.
Tuna without a can opener.
Yeah.
That is a brilliant, devastating analogy. You have the theoretical resource, but you are structurally locked out of ever utilizing it. You can't feed the defense industry with a pile of unrefined rocks. And this total reliance on these highly specific, heavily refined, smart metals brings us to a fascinating and honestly deeply troubling paradox. Because the exact same elements required to build a fleet of advanced supersonic stealth bombers or a billion new vibrant smartphones are the exact same elements that we are told are required to save the planet from catastrophic climate change.
This is what the author of our source text terms the green tech paradox. We are standing at the precipice of a future where we absolutely must transition away from fossil fuels if human civilization is going to survive. But the physical infrastructure of that sustainable post-carbon future, the towering wind turbines, the massive solar panel arrays, the millions of electric vehicles, demands absolutely staggering amounts of these rare metals.
Let's break down the mechanics of this, starting with wind turbines. We talked about Masato Sagawa earlier and his invention of the incredibly powerful neodymium iron boron magnet. When the wind energy sector started building massive offshore turbines, they faced an engineering problem. Older turbines relied on heavy, complex mechanical gearboxes to step up the slow rotation of the blades into high-speed rotation for the generator.
But gearboxes are heavy, they break down constantly, and sending a mechanic out to the middle of the ocean to fix them is incredibly expensive.
Right. So the industry shifted to direct drive systems.
And direct drive systems eliminate the gearbox entirely. But to generate electricity from the slow, direct rotation of the blades, you need a massive, incredibly dense magnetic field. You need Sagawa's permanent magnets. A single, modern, high-capacity offshore wind turbine can require hundreds of pounds of highly refined neodymium and dysprosium.
Hundreds of pounds for just one turbine.
And that is just one turbine. Then you factor in the electric vehicle revolution. EVs don't burn gasoline, they burn chemistry. They require vast, unprecedented amounts of lithium, cobalt, and rare earths for their high-capacity batteries and their high-efficiency electric motors.
And when you look at the projections, the math is simply terrifying. The United Nations has stated that to avoid the worst impacts of climate change, the world needs renewable sources to supply at least 50% of global energy by the year 2050. To hit those aggressive decarbonization goals, some industrial studies suggest we would need a 700% increase in global neodymium production and a staggering 2,600% increase in dysprosium production over the next 25 years.
Those numbers are astronomical.
But if you look at historical mining data, global production of these trace elements has typically only grown by about 6% a year. The physical reality of the mining industry simply does not match the utopian timeline of the green transition.
And this leads us to the darkest, most uncomfortable part of the paradox. We associate these technologies with a clean, pristine future. But the reality is, rare metals are green, but mining them is incredibly, profoundly dirty.
It's a tough truth to swallow.
To truly see the environmental cost of our clean energy future, the author takes us to the rural hills of Jiangxi province in China. This region is the global epicenter for the mining of heavy rare earths, specifically elements like the dysprosium required for those wind turbines and EV motors.
And the mining operation in Jiangxi is not some high-tech, surgically precise extraction. It is brutally primitive and ecologically devastating. Local villagers literally hike up into the lush clay hillsides and dig thousands of 8-foot deep holes directly into the earth. Then they pump massive amounts of ammonium sulfate acid directly into the ground.
The chemistry behind this is brutal. The heavy rare earths in Jiangxi are adsorbed onto the surface of the clay minerals. When you flood the soil with ammonium sulfate, the chemical reaction essentially washes the rare earths off the clay, allowing them to be collected in pools at the bottom of the hills.
But what does that do to the land?
It completely destroys the structural integrity of the earth. It creates vast, toxic, barren wastelands. It triggers massive landslides. The acidic runoff permanently poisons the local groundwater, destroys agricultural fields, and leaves behind severe acid mine drainage that will ravage the local ecosystem for generations.
We have a researcher mentioned in the text, Komi Harada from Japan, who actually quantified this destruction. He developed a metric to measure the total materials requirement, or what environmentalists sometimes call the ecological rucksack of a product.
I've heard of that.
He calculated the total hidden weight of the earth that must be violently moved, the fossil fuels burned, the chemicals deployed, and the toxic wastewater generated just to produce a finished metal. His math is devastating. To produce a simple 3-gram platinum wedding ring, it requires 3.6 tons of material waste and destruction.
3.6 tons for a ring.
To manufacture a single standard cell phone, it requires 31 kilograms of resources to be ripped from the earth.
So when a consumer in California or Berlin proudly buys a brand new hybrid car or installs a shipment of sleek solar panels on their roof, they are feeling very green and environmentally conscious locally. Their immediate air quality improves.
Sure, no tailpipe emissions.
But what they are effectively doing is exporting the pollution. They are exporting the carbon dioxide emissions, the toxic wastewater, and the radioactive runoff to the poorest, most vulnerable regions of the world where these metals are actually mined and refined.
I have to say, looking at all this data, it feels exactly like someone trying to go on a diet by eating low-fat cookies, but then deciding to eat 10 times as many of them because the label says they are healthy.
That's a depressingly accurate comparison.
We are collectively patting ourselves on the back for buying green technology, but we are physically ravaging the earth with acid and heavy machinery to pull materials out to build it. Are we actually making the planet better, or are we just shifting the destruction to places we don't have to look at?
It is the ultimate existential question of the rare metal age. And whenever this paradox is brought up, tech executives and politicians immediately point to recycling as the ultimate savior. They use buzzwords like circular economy and urban mining. They sell us the comforting idea that we can simply extract the rare metals we need from the billions of old, discarded electronics sitting in our drawers.
Right, the dream of infinite recycling. But the source text dismantles that myth incredibly quickly. The current reality is abysmal. Today, globally, we recycle less than 1% of many of these critical minor metals. Less than 1%. Why is that number so pathetically low?
Because the economics and the underlying thermodynamics of recycling complex electronics are an absolute nightmare. First, you have the design of the products themselves. Websites like iFixit have documented how modern smartphones are built with a built-in death clock.
Oh, planned obsolescence.
Exactly.
Yeah.
Tech companies intentionally design these devices using industrial glues, fusing the battery directly to the chassis, making them nearly impossible for a consumer to repair. They do this because their business model requires you to throw the phone away and buy a new one every 2 years.
But even if that glued-together phone manages to make it to a highly advanced e-waste recycling plant, you face a thermodynamic wall, right?
You do. You can't just toss a smartphone into a giant furnace and expect pure metals to neatly separate out. A modern circuit board is a microscopic, densely packed chemical lasagna of 60 different elements.
A chemical lasagna.
Yeah. If you shred it and apply intense heat or acid to extract the highly valuable gold or copper, the violent chemical process required to save those base metals usually oxidizes and completely destroys the trace amounts of dysprosium or tantalum. The very act of extracting one metal often chemically ruins the chance of extracting another.
So we are stuck in a seemingly impossible bind. Mining new metals is environmentally toxic and geopolitically dangerous. And recycling the metals we already have is currently a thermodynamic pipe dream. So how on earth do we prosper in this era? What are the author's actual actionable solutions for surviving the rare metal age without destroying the planet or stumbling into a global resource war?
Well, the author outlines 3 primary paths forward. The first path is intellectual humility. We have to fundamentally acknowledge that human beings are terrible at predicting the future of technology. The text cites some amazing historical blunders to prove this point.
Oh, I love these.
Right. In 1946, Darryl Zanuck, the head of 20th Century Pictures, confidently predicted that television would fail within 6 months because people would get tired of staring at a plywood box. Or Ken Olsen, the founder of Digital Equipment Corporation, stating in 1977 that there was absolutely no reason anyone would ever want a computer in their home.
Those quotes are hilarious now, but they prove a vital point. If the greatest minds of the past couldn't predict a smartphone, we cannot possibly predict what the next world-changing invention will be. And therefore, we cannot predict which obscure, currently useless rare metal will suddenly become the most sought-after resource on Earth.
Precisely. So the solution is that governments and industries must proactively maintain flexible, resilient, and diverse supply chains for all elements on the periodic table, not just the ones that are popular today. We can't afford to let processing capabilities atrophy just because a metal is currently cheap.
Okay, so humility and flexibility solve the front end, getting the materials. What is the second path? How do we address the back end, the massive waste?
The second path is extending product life cycles. We have to aggressively force technology companies through legislation, if necessary, to design their products for modularity and repairability. We have to end the toxic culture of treating highly complex, rare metal-laden devices as disposable trash.
Make things that last.
Exactly. If your battery degrades, replacing it should be as simple and cheap as changing a light bulb. Keeping a device in service for 5 years instead of 2 instantly halves the mining burden on the Earth.
The right to repair movement is critical to our environmental survival. And the third solution?
The third solution is entirely geopolitical. The author advocates for the creation of an international materials agency. If you look back at the oil shocks of the 1970s, the global community panicked, but then they came together and created the International Energy Agency to track, manage, and secure global oil flows. We desperately need a similar, highly empowered, independent global body for rare metals.
So you got to referee the whole thing.
Yeah, we need an organization that can collect transparent statistics, audit global reserves, enforce environmental standards, and crucially, provide a diplomatic forum to de-escalate tensions and prevent the next great global conflict over these essential elements.
Okay, let's take a deep breath, step back, and just look at the sheer scale of the journey we have taken today. We started with the simple weightless tap of a finger on a piece of glass, and that tiny electrical disturbance pulled us across the entire globe. We traveled to a feeding thermal resort in Brazil, sitting next to a benevolent corporate fortress. We stood inside a freezing, toxic, post-Soviet factory in Estonia, watching chemists try to unbake radioactive cakes. We watched an invisible, silent embargo over a fishing boat send massive shockwaves through the tech world, only to realize that the delicate steering fins of a supersonic stealth fighter and the massive spinning blades of a green wind turbine depend on the exact same highly fragile thread of dirt.
It completely reframes how you look at the physical world around you, doesn't it? The digital age is sold to us as something ethereal and wireless. We talk about storing data in the cloud, surfing the web, but it is all a physical illusion. The modern world is deeply, heavily, and violently tethered to the dirt.
It really is.
Every single time you upgrade your phone for a slightly better camera, every time you turn on a high-efficiency LED light bulb, you are physically pulling on microscopic strings that reach deep into the most volatile, toxic, and complex corners of the planet.
It makes you wonder deeply about the future. And I want to leave you, the listener, with a final provocative thought to mull over as you go about your day, building on everything we have explored. As our world becomes increasingly desperate for these trace elements to build our green, decarbonized future, and as the traditional mines in places like Brazil or China inevitably run dry or become simply too politically toxic to operate, what happens then? What happens when the richest, most densely concentrated mines on Earth are no longer located in a volcanic crater in the jungle? What happens when the highest concentration of rare metals on the planet is actually sitting in the massive, toxic, forgotten electronic landfills buried right under our own cities?
That reality completely flips the global geopolitical map upside down. The resource advantage shifts from the nations with the largest geological reserves to the nations with the largest technological graveyards.
Exactly. Will the next great, world-defining global conflict be fought not over foreign land or disputed ocean borders or oil fields, but over the recycling rights to our own massive technological landfills?
Yeah, right.
Will the superpowers of the late 21st century be the ones who finally figure out the thermodynamics of urban mining? Will we literally be mining our own toxic trash to build the future? It is absolutely something to think about the next time you are holding that little piece of weightless magic in the palm of your hand. Thank you so much for joining us in this deep dive. We'll see you next time.